All right, we have two differential equations here to sketch the slope field for. The first one is dy dx is 2 minus y. And then we have dy dx is equal to x divided by y. So go ahead and pause the video, give those two a try, sketching those out. We'll see if we come to the same thing. All right, so dy dx is equal to 2 minus y. There's no x involved here, so what I want to do is I want to plot along these y equals lines, because I know that along that line, it's going to have the same slope at every point along here. All right, so let's start with y equals 0. So when y is equal to 0, 2 minus 0 is 2. So all along here, we have a slope of 2. And when y is equal to 2, negative 2, 2 minus a negative 2 gives me a slope of 4, so more steep. Along that line. And let's do y is equal to 1. So 2 minus 1 is 1, so slightly less steep here. And when y is equal to 2, I get 2 minus 2 is 0, so the slope is 0 here. So this is flattened out. Okay, and let's do y is equal to 4. So 2 minus 4 is a negative 2. So downhill slopes along here. Okay, and I can do some more lines in here, but I think this gives me enough to have a good sense of what's going on. All right, so it looks like I have some lines that are kind of curving up this way and some that are probably curving down this way. So let's take a look at these initial conditions. So I want to sketch the solution curve for each one of these. So I'll have 3 lines when I'm done. So I'll start with x is 0, y is 1. So that is right here. Okay, so this is my slope here. So it's telling me to head off in this direction. Once I start heading in this direction, now it tells me my slope is flat. Okay, so it looks like, and it's going to stay flat all along here everywhere I go. So this looks like about here. And then on this end, I go this way. Now it looks like I need to course adjust and go a little steeper. And then this looks even steeper still. So it looks like there is the solution curve for number 1. Put a Roman numeral 1 here. Roman numeral 2 says x is 1, y is 0. So that's right here. Right, so this tells me to head out in this direction. And then it looks like I need to flatten out a little bit, so I'm a little less steep. And I'll head out some more. And now it looks like I'm hitting the spot where the slope is 0. All right, so I'm going to join these guys and kind of flattening out. If I do this end of the curve, I'll head off in this direction. Okay, now it looks like I've got to get more steep. So there is my second solution curve. All right, and then third solution curve, y is 3x is 0, so that's going to be up here. All right, and I didn't put a point here, so let's figure out what that slope is quick. So that's 2 minus 3, so that's a negative 1. Okay, so it looks like this. If I follow that out this way, kind of the next thing I run into is a slope of 0. So I need to flatten this out. And it's just going to stay with a slope of 0 everywhere along here. Has that really flat slope. And then if I head back this direction, I get here, it looks like I need to be a little bit steeper. So I'll course correct to become a little steeper. Okay, and there is my third initial condition. So there are 3 solution curves, one for each of those initial conditions. And then it says, what is the long run behavior of y? So as x gets really big, is this thing settling down to a specific value? Yeah, it is. Looks like it's settling down right here to y equals 2 on this nice flat spot. So limit as x goes to infinity of y is equal to 2. So it's our long run behavior. Right, and then let's take a look at number 3. So x over y. This is a little more work to graph because we have to account for both variables changing. So let's let's do ourselves some favors here and start with some of the easier places to plot. One of those would be when x is 0, this whole fraction is 0. So I'll start with x equals 0. That'll be nice and easy to plot along here. Okay, and similarly, when y is equal to 0, this is actually undefined. And that's going to give us little vertical lines along here. Since vertical lines have an undefined slope. Okay. Let's see, let's try x is equal to 1. So this means I'll do 1 divided by y. So 1 divided by, here y is equal to 1 is 1. 1 divided by 2 is a half, it's a little flatter. 1 divided by 3 is 1/3. Okay, so this looks like it's kind of flattening out. And we can do the same thing down here too. So now I'm divided by just negative y. So I get negative 1, negative 1/2, negative 1/3, negative 1/4. So kind of flattening out. And x is negative 1. So negative 1 divided by y is 1. Gives me a negative 1. Negative 1 divided by 2 is a negative 1/2. So all these slopes up here are going to be negative, and they're just getting smaller and smaller. Okay, and then same thing here. So this is negative 1 divided by negative 1, so that's a positive 1. And then this will be negative 1 divided by negative 2, so that would give me a positive 1/2. So these are going to be positive slopes, but getting less steep as we go along. All right, I kind of see this line here, and it makes me think I should plot along y equals x. So when y is equal to x, those slope lines are all going to be 1. Or the value of that slope is 1. And when y is equal to negative x, I'll get a slope of negative 1. Okay, and let's see, I feel like I have an okay sense of what's going on here and here, but I don't have anything over in these two triangles. So let's take a look at plotting something in there. Let's do y is 1. So this will be whatever the x value is divided by 1. So when x is 2, 2 divided by 1 is 2. So steep, steeper. So these are all getting much steeper. And these will be, this is negative 2 divided by 1. So that's a negative 2. These are also, oops, getting steeper. And then y is equal to negative 1. So this is 2 divided by negative 1, which gives me a negative 2. So these are also getting steeper here. And same idea here. So it looks like I've kind of got these little like semicircles floating through. Not really circles, but. All right, so that gives me a good idea of what my slope field looks like. You can certainly plot more of these to get a better idea of what's going on. I've kind of done enough of these that I can see this is flat, this is going positive, this is going negative, so it's looking like this is going to loop around on me. All right, so let's look at these initial conditions. So initial condition 1, x is 0, y is 1. All right, so this is flat. And then I hit this line here if I travel a little bit, which has a slope of 1. So I'm going to adjust my slope. And it looks like all along here, my slope stays pretty close to 1. So seeing that go on. And then on this side here, if I travel a little ways, I hit a slope of negative 1. So I'll course correct. And all along here, actually, my slope is going to stay close to that value of negative 1. I'm looking at something that looks like that. And that is my first set of initial conditions. Y is 0 when x is 1, so that's right here. So again, there's my slope there for that vertical line. I hit here, now I need to course correct, change my slope, and then my slope stays pretty constant along here. Same thing here, go straight down until I hit here, and I need to course correct to match that slope of negative 1. So there's my second set of initial conditions. And then my third set of initial conditions, x is 0, y is 3. So I go here, and now it looks like I have a little bit flatter. Well, this is flat, and this is a little less than flat, so it's a little slightly positive. That's fine, we'll head out in this direction. And it's going to start curving because now it's going to get closer and closer to 1. So I'm getting something that's going to loop up like this. So start flat here. Looks like I have a little bit of a negative slope, so I'll course correct. And it's just going to get a little bit more negative as I approach the value of the slope being -1 there. So here is my third set of initial conditions. Okay. So there's our picture with our 3 solution curves. So each one of these lines is the solution curve for the differential equation with that set of initial conditions. All right, so now we're asked, what is the long run behavior here? And so remember I said that as I was coming along here, I'm approaching this slope of 1 where this is where y is equal to x. So as y gets really big, the value of y is approaching the value of x. It's approaching this y equals x line or this y equals negative x line. So my limit here, as x goes to infinity of y, is equal to plus or minus x. Okay, so a little bit different than probably how you've really used limits in the past, just because we're doing something a little bit different. But what you're really looking for is there a value as y gets really big that we're approaching here? Or as x, I'm sorry, let me rephrase that. As x gets really big, is there a value that y is approaching? Is there a value our solution is approaching? Okay. All right. All right. Since differential equations are used to model many real-life situations, the question of whether a solution is unique can have great practical importance. And by that we mean, is there just one answer to the problem? So if we know the velocity of a satellite is changed and we know how it's changing, can we predict its velocity at a future time? If you've got 2 or 3 or 5 different answers for that, that's not very helpful. You want one specific answer to that. So that's what we're looking for when we say that there's a unique solution. In the language of differential equations, an initial value problem, which is often abbreviated as IVP, almost always has a unique solution. One way to see that is by looking at the slope field. So imagine at the starting at the point represented by the initial condition, which is what we've done in these. Through that point, there's usually a line segment directing you in the direction of that solution curve. So you follow that out and you trace out your solution, which is what we've done here. In general, at each point, there's only one line segment and therefore only one direction for the solution curve to go. The solution curve exists and are unique, provided we're given an initial point. So this is a big topic in mathematics. How do we know we have a solution? Does a solution exist? And if it does exist, is it unique? Okay, so those are huge questions in the field of differential equations and in numerical methods. It's something if you take more advanced math courses, you'll definitely be taking a look at.